This lesson goes with Chapter 1, Driving the Roads, Section 3, and we'll be investigating average speed. There are many ways that you can describe motion. One of the ways is using strobe diagrams. These are also called motion maps. A strobe diagram is when a photograph is taken and the shutter speed is very, very rapid, so you can watch the motion or the path of a moving object in a series of pictures next to each other. The strobe diagram shows where an object is for every period of time. So every time you see the dancer, that was the position that the dancer was in at that moment in time. Each of these motion maps or strobe photos show an object that's moving at a constant speed. The object is moving the same distance every second. When objects are moving at a constant speed, the same amount of time elapses between each image and the next. The object is moving the same amount of distance each second. We see that in each of these diagrams. The car is here, it was here, it was here. Those distances are all equal. Same thing with the skateboarder. These distances are equal. So we can see that the object is moving the same amount of distance every second. Here we have 4 different motion maps. A map showing a soccer ball, a car, a runner, and a skateboarder. Each motion map or strobe diagram shows a different type of motion. Let's talk about which type of motion is shown in each strobe diagram. Question 1 asks, which motion diagram shows an object slowing down? How would we know if an object is slowing down? When an object slows down, the pictures are going to get closer together. The object is not traveling as far every second. So therefore, the motion diagram that shows the object slowing down is going to be the car. Here, the cars are getting closer together in the picture. The next question asks, which motion diagram shows an object speeding up? How would we know from a motion diagram if an object is speeding up? If an object is speeding up, then in the motion diagram, the object would get further and further apart. So the object that's speeding up is the runner. There's more space showing where that person was every second as the time goes on. The next question is, which motion diagram shows a stationary object? So we're looking for an object that's standing still. This, of course, is object A, the soccer ball. As time passes, every second, the soccer ball is staying in the same place. So there is no other pictures of the soccer ball alongside because the soccer ball is in that same place every time. And then finally, which motion diagram shows an object moving with a constant speed? Constant speed means the object is traveling the same distance every second. And of course, that is shown in the skater. The important thing to remember about strobe diagrams or motion maps is that they show the position of an object every second. So where the object is located every second that passes. You can also describe motion using an equation. The equation to find average speed is the average speed is equal to the distance traveled, which means how far did the object go, compared to the amount of time that has passed. So for how long? we can look at that equation written with symbols this way. Means the same thing as the words, but it's in symbol form. So the V, av, means the average speed. Triangle D means the change in distance or the change in position. Triangle T means change in time, okay, or what's known as the elapsed time. And that weird triangle, why is that there? The Greek letter delta, which is that triangle, is used to mean change. So anytime you see a triangle next to a letter, change in velocity, change in distance, change in time, it's just a short way of writing it so that we don't have to write every single time change in velocity or change in distance, etc. It makes it a lot faster for us to use the symbols like this. So let's try a sample problem. You are driving a distance of 400 miles or about 640 kilometers. And that takes you 8 hours. What's the average speed? You can use the equation V_av, or average velocity, average speed, is equal to the change in distance divided by the change in time. What are we given? We're given the change in distance is 400 miles. We're given that the change in time is 8 hours. It's always good to write down the things that you know from the problem. What is the problem telling you? It's telling you how far you travel, and it's telling you how much time that takes. Then you use your equation, write down the equation, and you plug in the information. So the 400-mile distance, plug in for D, and the 8 hours of time, plug in for T, and then you simply do the math to solve. 400 divided by 8 is equal to 50. So your average speed is equal to 50 miles per hour, or we can write that as mph. That means every hour you travel, you go 50 miles. That's what miles per hour means. Now this equation works great if you're trying to figure out the average speed. But what if I have information and I want to figure out the time? Or what if I have information I want to figure out how far I went? I need to be able to rearrange this equation. Here's a simple tool to use to rearrange the equations. If I am trying to find average speed, we use the V equals D over T equation. But if I want to find out the distance, then I can rearrange this equation, and now I have D is equal to V times T. And if I want to find the amount of time, then I have time equals the distance divided by the velocity. So these three equations can be used in different ways to find different pieces of information. You can also use what I call the circle method. Sometimes this is easier for people to use. So this has the distance, and it has average velocity, and it has the time. And the way you use a circle is if you're trying to find average velocity, like the first equation at the top, you need to know D and T. And since they are above each other, you divide. D divided by T. If you are trying to find the distance, D, then you have the velocity multiplied by the time. Since they're next to each other mathematically, you would multiply those things. And if you are trying to find the time measurement, you would use the distance divided by v for speed. Again, they're on top of one another, so you divide them. Another way of showing motion is by using a distance time graph. A distance time graph is a very visual way to represent the motion of an object. In this graph, we have an object that is moving at a constant velocity. The constant velocity is 50 miles per hour. Notice on the y-axis we have distance measured in miles, and on the x-axis we have the time measured in hours. By looking carefully at the graph, you can see that at a time of 1 hour, the car had traveled 50 miles. After 2 hours, 100 miles. After 3 hours, 150 miles. And after 4 hours, 200 miles. And when we connect the dots on the graph, we see that nice line for the distance time graph. It shows the motion of the object was constant because there is a straight line to the graph. Here are a few distance time graphs. Use the graph to determine the type of motion shown. Is the object standing still? Is it moving at a constant velocity? Do you know anything about the direction the object is moving based on the graph? Please write your answer on today's page in your binder. So to summarize, let's again go back to each of the 3 methods that we use to describe motion. First, we learned about strobe diagrams or motion maps. These show visually in a picture the relationship between the position of an object, where the object is, in a certain amount of time. Second, we talked about equations. Equations show mathematically the relationship between position or distance and time. Third, we talked about distance time graphs. These are a visual representation of the relationship between distance and time. Each of these can be used to show the same motion. They just show them in slightly different ways. So please take a few minutes to do the review and answer these questions on today's page in your binder. Remember to go back and review this tutorial as many times as needed and ask questions if you have any. Thanks!